So, hi, today we are going to be solving some hard chemistry MCQs for our practice. They're taken from November 2020. And I've taken these MCQs from the examiner reports. These were the specific questions about examiners given the comments, and these were the questions found challenging by the candidates. So, let's solve all these questions from this paper. And that's going to be a really good practice, and that's paper 12 for November 2020. So the first difficult question was this one, and I have written the key concept of the question as well. So first let's look at the question, and then we're going to look at the key concept. The question says chromatography can be used to separate and identify dyes present in a mixture. Okay, we know chromatography, it's a separation technique, and we use it to separate and identify the dyes and to know the solubility of a substance. Okay, which statement is correct? Okay, we're given with three statements, and this question is a bit tricky, okay? So I'd like you guys first choose your answer before I tell the correct ones. So A statement says that a dye with an RF value of 1.2 can be present in the mixture. Okay, I tell you one thing today. RF values cannot be greater than 1. RF values, cannot be greater than 1. Okay? Greater than 1, impossible. Okay, that's not possible to have an RF value of greater than 1, and if you have, that means that that's wrong. So 1.2 RF value is not possible. Why it's not possible? Because you just have to look at the equation. Distance traveled by the substance cannot be greater than the distance traveled by the solvent front. That's why you cannot have an RF value of greater than 1. So technically this is incorrect. Moving on to option 2, which says that a dye could have different RF values in different solvent if a different solvent was used. That's correct. You should remember that different dyes have different RF values. Okay, that's what we know. But a same dye, okay, if I have this dye, that's for example, I call it dye R. If I do a chromatography of dye R using water, I will get a different RF value. And if I do a chromatography of dye R using alcohol or my ethanol, so I'm going to give it, if this is R and this is my ethanol, I'm going to get a different RF value. So if I change my solvent, my RF value is going to change. Okay, next statement, that's extremely confusing. All blue dyes have the same RF value. That is not correct. There can be a million or a billion blue dyes present on Earth, but all of them could have different RF values. They could be made up of different substances. Okay, and chromatography can only be used for colored substances such as dyes. No, it can be used for uncolored substances such as amino acids as well. And you commonly use your chromatography for your amino acids, and you use a locating agent. If you want to name a specific locating agent, that's ninhydrin, and this locating agent makes the dyes visible. So amino acids are, kind of transparent and visible, and then you add this ninhydrin thing and they're visible. So the key concept in this question, which I felt was challenging, look, first, an RF value greater than 1 is impossible. That's the first key concept. Okay, you cannot have an RF value greater than 1. The second key concept, uncolored substances can be separated using a locating agent. So if the substance is not colored, that does not matter. You can use it using a locating agent. The third point to be noticed was same substance can have different RF values in different solvents. The solvent does not, really play a difference. For example, if you have a same substance, it can have, no, a solvent plays a difference. If you have a same substance in different solvents, it's going to have different RF value. Same substance will have different RF value in water, a different in an acid, a different in a, an alcohol or anything. And the third or the fourth or the most important thing I guess was that a million dyes chemically different can all be blue in color. So it's not necessary that all blue dyes have the same RF value. Color is not something that makes substance same. For example, a lettuce and an oregano that's used for cooking, I guess, are both green in color. Are both green in color, but they're not both the same color. But are they both the same? No, they are not the same. So both are green in color, but they're different substances. That is why all blue substances cannot be, having the same RF value. They can have different RF values because they're chemically different. So that is what you have to understand. These are the key concept of this question. Moving on to the next difficult question, which was this one. A sample of magnesium hydroxide has a mass of 4.63 grams. How many moles of magnesium hydroxide are present? Okay, now if we simply think of this question, we know that moles equal to our mass upon our MR. and mass is 4.63, and mR we can take of magnesium, and then we can take off hydroxide as OH, and that's going to do the job. But most people struggle with one thing: they forget about the formula of magnesium hydroxide, and that's where the key concept of this question comes in. The formula of magnesium hydroxide is very important. The formula for MgOH is MgOH2. Why? Because magnesium has a charge of 2 plus and hydroxide has a charge of -1. This -1 comes here, this 2 goes there, and you have MgOH2. So that's what you need to realize while getting out the mR. And moles equals to mass upon mR. That's what we know. So let's get it. Magnesium, mass mR. To get the mR, magnesium is 24. Oxygen is 16, but we have 2 oxygen, so that's 2 times 16, and plus hydrogen is 1, so 1 times 2 is 2. So let's do it. It's 24 plus 16 times 2 plus 2, and that's going to give you an mR of 58. So 4.63 upon 58, 4.63 divided by 58, 4.63 divided by 58, and that's 0.0798 moles. So 0.0798 moles, and I guess that's option B. So the key concept in this question was this thing that you had to learn to make formula. Okay, now moving on to the next difficult question. I have to move this thing over here, and this was the next difficult question. Let's see, the concentration of which statement is correct. Okay, the concentration of a solution is expressed in dm cube per mole. That's incorrect. We express it in mole per dm cube. So incorrect. The empirical formula of a compound always gives the actual numbers of each type of atom in one molecule. That's incorrect. It does not give you the actual numbers. What it really gives you is the simplest whole number ratio. So simplest whole number ratio. That is what you get from empirical formula, not the actual. The actual numbers are given by your molecular formula. Okay, the molecular formula of a compound always contains more atoms than the empirical formula. That's absolutely incorrect. Some compounds can have the same molecular and empirical formula. For example, I give you a compound like C10, H60, H63, and O21. So now tell me what's the molecular form. This is the molecular formula. What's the empirical formula? It's going to be the same thing, because these all cannot be cut on one table. So this statement is incorrect. Sometimes they are equal. Okay, the relative atomic mass of an element is the average mass of one atom of that element divided by 1/12 of the mass of a carbon-12 atom. Considering that all these statements are wrong, D has to be the correct option. So the relative atomic mass is the average mass of one atom. That's correct. You take the average mass and divided by 1/12 of the mass of a carbon-12 atom. 1/12 of the mass of a carbon-12 atom simply means 1. Okay, so that's correct. D has to be correct, because for example, if you're taking magnesium, you take mass for all the magnesium isotopes. That's 24, and you divide it by 1. This entire line, which seems very confusing, 1/12 of the mass of a carbon-12 atom simply means 1 equals to 24. So that's the AR for magnesium. So moving on to the next question, which says that the equation shows the production of iron by the reduction of iron 3 oxide. Okay, you have iron 3 oxide and it's reducing to iron. Why is this a reduction? Because you need to look at the oxidation numbers. Over here iron has an oxidation of 3 plus, and over here iron has an oxidation of 0. So what basically happening is there is a decrease in oxidation number, and a decrease in oxidation number is called reduction. So iron 3 oxide is being reduced to form iron. So that was the concept. Now let's look at what the question is asking. 80 tons of iron 3 oxide produces 50 tons of iron. What is the percentage yield? Okay, I guess many people gets confused with this. Okay, now I need to explain you guys one thing. 80 tons of iron 3 oxide is what we have taken. And now this 50 tons of iron that's being produced is what happens inside the laboratory. Now you need to keep in mind one thing. What you need to keep in mind is it's not always that you're going to get 50 tons. You can get a different yield as well. This is your yield, what you got in laboratory. But in reality, the yield is different on theory. The yield, the theoretical yield is basically the yield you get on paper. And this is basically the yield you got in laboratory. when you perform the experiment, and that's different from what you get on paper. So what do I get in paper? Let's see. Okay, when I take this, let's calculate the mass of this entire thing. 2 times iron, which is going to be 2 times 56. Okay, this Fe2O3, what's the mass? 2 times iron is 56 plus 3 times 16. So 2 times 56 plus 3 times 16. That's going to give me 160. So I have 1 Fe2O3, the mass is 160. And for 2Fe, that means 2 times for 2Fe, it's going to be 2 times 56. Let's see what I get. That's going to be simply 112, and that's going to be 11. So 112. So that means that when I use my 160 grams of my Fe2O3 iron oxide, I guess 112 grams of iron. So that should exactly be what should happen. So now I'll make my percentage. I'm going to say that my Fe2O3 ratio my Fe according to this equation. If this equation is true, then if I use 160 grams of my Fe, I should get 112 grams of my iron. So accordingly, when I am using my 80 tons of Fe2O3, my iron 3 oxide, if I'm using 80 tons of it, I should get my X tons of iron. So let's see what X comes out to be. But in reality, I got this. But on paper, when I'm performing calculations, I'm getting this. So let's see what I get on paper. So it's simply going to be like this. X will be equal to 80 times 112 divided by 160. So X comes out to be 80 times 112 divided by 60. 80 times 112 divided by 160, and that's going to be 56. So in reality, I should get 56. I should get 56 tons or 56 grams. But because we are doing all things in tons, so we have to write tons over here. In reality, I should get 56 tons, but unfortunately, I only got 50 tons, so that's unfair. 6 tons are being lost over here. So what's the percentage yield? What's the yield? So in reality, I should get this. In lab, I got this. When I performed in lab, I only got 50 tons, but on paper, I got this. So it's going to be my yield, which should be there, my actual yield, which should be 56 upon my this is my theoretical yield, which I got in theory, upon my actual yield, which in reality I got in laboratory, which is 50, whereas I should get 56 if it was 100% pure yield times my 100. So that should give me, I guess, 89. This should give me 89%. Let's confirm it. 50 divided by 56 times 100, and that gives me 89. So that means my answer should be 89%. And that's the key concept in this experiment, in this question. What's the key concept? The actual yield upon your theoretical yield. Actual yield is the yield you get in laboratory or when you do the experiment, and theoretical yield is the yield that I got on paper, which was 56 when I did this thing. Okay, times 100. Actual yield is the yield you get in reality. Theoretical yield is the yield you get on paper. That's very important. People confuse what's the actual, what's the theoretical. You just need to keep in mind actual, what I do. Theoretical, what is on paper. In chemistry, in all experiments, we never get 100% product. Okay, we always get the less product than on paper. On paper, I got this 56 tons, but in reality, I got 50 tons. Always remember that in chemistry, there is never 100% yield possible. That's rarely possible. So what we get actually in lab is different from what we calculate. So what I do in lab is going to be different from the paper calculation. That was the key concept in this question. Okay, moving on to this question. The diagram shows the electrolysis of a mixture of aqueous copper 2 nitrate, CuNO32, okay, and aqueous copper nitrate, aqueous silver nitrate. Electrodes X and Y are inert. Okay, we are taking inert electrodes. We have silver nitrate and copper nitrate. Copper is above silver in the reactivity series. Why have they told this? Because when we are discharging our positive ions, our copper and silver ions, when they're going to get discharged, we have to look at the reactivity series. Because copper is above, that means it's difficult for copper to discharge, because as you go up it becomes difficult for you to discharge. So silver is going to discharge in preference. Okay, let's label our anode and cathode. This negative one, that's definitely going to be the cathode. So this one right here is your cathode, and this positive one right here is your anode. So this is going to be, X is going to be the anode and Y is going to be the cathode. Let's read. It can be deduced that 1 is initially deposited at electrode this. So copper or silver is going to be deposited at this Y, because at cathode you have your positive ions, because it's negative, so positive ions going to attract, and silver is going to be deposited because silver is below in the reactivity series, and the more below you are, that's how you get discharge. So obviously silver, because look, the more less you are in the reactivity series, the more easier it is for you to gain that electron and get discharged, because for positive ions to get discharged they need to gain electrons. For silver it's easier to gain that one electron compared to copper. So it's going to be question number D. The key concept over here is, first you had to identify the negative electrode is your cathode. This right here, Y was your cathode, first thing. And in metals, the less reactive you are, the more chance of you getting discharged. So silver formed. That was the key concept in this question. Moving on to the next difficult question, which was this one right here. Silver is below hydrogen in the reactivity series. Why? They have told you this thing. Silver is below hydrogen. This means if this is your hydrogen, this is your silver. That means silver cannot displace hydrogen because hydrogen is more reactive. Which row describes the chemicals used and the method of separation used to prepare a pure sample of silver chloride? Okay, now they have given you some chemicals, silver and hydrochloric acid. Look over here. Silver is less reactive than hydrochloric acid. So what's going to happen? Ag plus HCl. So that's what you're doing. But the reaction is not going to take place. No reaction. Why the reaction is not going to take place? Because of this statement that they've told you when the question began. The silver is below in the reactivity series than hydrogen. So basically this silver cannot displace this hydrogen over here, and it cannot form AgCl. Okay, so that's why there's going to be no reaction. Because what happens if it was zinc? So what would zinc do? Because zinc is more reactive than hydrogen, zinc would take place of hydrogen. Instead of hydrogen, you'll form zinc over here, and it's going to form zinc chloride. But over here, because silver is less reactive, it cannot displace this hydrogen. Hence, this is not going to take place. This reaction is not going to take place. Well, you can use silver nitrate and hydrochloric acid, and you can use this. Why this is going to work? Because look, when you have two salts, a double displacement reaction takes place. Let me explain you what do I mean by double displacement. For example, right now over here you have silver nitrate, which is AgNO3. Okay, I said that this silver cannot displace the hydrochloric acid, hydrogen in hydrochloric acid. That's correct. But this H right here can displace the silver and form HNO3, which is nitric acid. So what this H is going to do, it's going to displace silver. So this silver comes over here to form AgCl, and as AgCl, this reaction is going to take place. So we erase no reaction, and we're going to form our AgCl, which is going to be a solid. Why a solid? Because AgCl is insoluble, plus HNO3. And now, since it's insoluble, it can easily be separated by filtration. So the option is going to be option D. The key concept in this question was, first, silver cannot displace hydrogen from hydrochloric acid because silver is less reactive. And the second key concept was, learn solubility rules. That AgCl is insoluble. We prepare insoluble salts by precipitation. This involves filtration. Okay, precipitation means we take two soluble salts. Over here, we took two soluble salts like silver nitrate and HCl. We formed an insoluble salt, and that's separated by filtration. I don't know why these questions were felt difficult by candidates. They're really easy. I just don't know. But still, let's continue with question number 27. These are all according to the examiner reports. An atom of which element has the same electronic configuration as an atom of an ion of strontium? Okay. The key concept is that which atom will have the same electronic configuration. What we're looking for is an electronic configuration as an atom of an ion. We're looking for an ion of strontium. Look, Ions have noble gas electronic configuration. What happens is, for example, this is my atom, which has 4 electrons, and it basically gains 4 more electrons. Okay, it gains 4 electrons. It has a charge of -4. Why would this ion gain 4 electrons? To get a noble, this atom gain 4 electrons to get a noble gas electronic configuration. So once this atom has formed an ion, it gets a noble gas electronic configuration because it has full outer shell electrons. So the thing you need to understand is, when calcium, it loses 2 electrons, what does it become? It become a noble gas. It has an electronic configuration of a noble gas. So ions have a noble gas electronic configuration. So a strontium ion is going to have a noble gas electronic configuration. Right now over here, calcium is not a noble gas, so we're going to cross calcium. Secondly, selenium is not a noble gas. Rubidium is also not a noble gas. We only have one noble gas in all the options, which is B, which is going to be krypton. And if you don't understand it, okay, I'm going to explain it to you using the periodic table. Now you need to look over here. Look, they told you a strontium ion. Okay, now you need to realize that strontium is in period 5. Okay, strontium is in period 5, meaning it has 5 shells, and because it's in group 2, that means in the last shell of strontium, for example, this is the last shell. Okay, period 5 means 5 shells: 1 shell, 2 shell, 3 shell, 4 shell, and 5 shell. Okay, I've drawn 5 shells. In the last shell, it is 2 electrons. Okay, in the last shell, strontium has 2 electrons. Now when it forms a strontium ion, these 2 electrons gets vanished or goes away, and it forms a 2 plus charge. And what happens now? It has 1, 2, 3, 4 shells left. And now in the last shell, strontium has full 8 electrons. And how many shells does strontium have? 1, 2, 3, 4. From 5 shells, it got 4 shells, and the last shell has 8 electrons. Okay, so we go to period 4 and we see that krypton has 4 shells, and in the last shell, krypton has 8 electrons. So that means a strontium ion and a krypton atom are going to have the same electronic configuration with 4 shells and 8 electrons in the last shell. Okay, I hope you understood this thing. This was a bit tricky, but you just had to realize that ions have noble gas electronic configuration, and period 5 loses 2 electrons, so 1 shell lost, and now it has the same as krypton. Electronic configuration. Moving on to the next question, which says that metals have high melting points. Okay, what is the reason for this? Okay, you need to realize that in metals, you have to break the metallic bonds. A metallic bond is an electrostatic force of attraction between the positive metal ions and the negatively charged C of delocalized electrons. So what's the electrostatic force of attraction? These are the positive, metal ions. You have positive metal ions, and these are the delocalized electron, and there's a force of attraction holding these both together, and this force of attraction is known as your electrostatic force, and that is what you need to break when you are breaking a metallic bond. So they have high melting and boiling points because the atoms are joined by strong covalent bonds. There are no covalent bonds in metals. They have strong force of attraction between the negative ions, not negative ions, positive ions, not negative ions. Force of attraction between the positive ions and delocalized electron. This one's correct. So the key concept in this question was this thing. Okay, moving on to the next question, which says that gas X is present in dry air and may contribute to global warming. What is X? Okay, may contribute to global warming and is present in dry air. So the composition of dry air, we know we have nitrogen, N2, we have oxygen, we have CO2, and greenhouse gases, we know it's CH2 or CH4. So it is either methane or carbon dioxide, but methane is not present in dry air, it's carbon dioxide. So we should know that carbon dioxide contributes to global warming. So it's going to be our carbon dioxide, but we have no carbon dioxide option. We have carbon monoxide, we have methane, we have nitrogen oxide, and we have sulfur dioxide. If we would have carbon dioxide option, that would be very good, but the problem is we don't have an option. So we have to go with methane, because methane is also a global warming gas, which is a greenhouse gas. So you just had to learn the qualities of all the gases, that CO is a toxic gas, CH4 causes global warming, carbon dioxide also causes the same thing, NOx or nitrogen oxides cause acid rain, photochemical smoke, and respiratory problems. This thing is according to the syllabus, so kindly learn it. And sulfur dioxide causes acid rain. So these were all the effects of all these gases, and that, I guess, was something you had to rote learn. moving on to this question, which was, I guess, found really, was really tricky. Propane undergoes substitution reactions when mixed with chlorine gas. Okay, we know that propane is an alkane, and alkanes are going to undergo substitution when you mix them with chlorine, because chlorine is going to replace that one hydrogen. From then, in the presence of UV light, why? Because UV light provides the activation energy for this reaction to take place. And what is activation energy? It is the minimum amount of energy that the colliding particles must have in order to react. When two particles collide, if they don't collide with the activation energy, they cannot form the product. To form a product, the particles need to react with activation energy. Okay, which compound could be formed when propane and chlorine are mixed in the presence of UV light? Okay, let's draw the structures of all these to understand that what can be formed when propane and chlorine are mixed. So we're going to draw these structures of all of them to understand. So I've written the names of all these compounds over here. Let's draw the structure. So first we have CH3. Let's draw. We have C and we have H3. Let's be quick. Then we have a C. Then we have Cl2. So one Cl above and one Cl below. And then we have CH3. So H, H, and H. So this is the first structure. The second structure was CH2. So H, H. And there was a Cl. Then again CH2. So H, H, and then a Cl. So that was the second structure. The third structure was, we have a CH3, H, H, H. Then we have a CH2, and then again we have a CH3, I guess like this, and then we have a chlorine. For chlorine, we don't have any place, so I guess we have to might place it over here because it's with the carbon. So that's clearly telling us it's incorrect. But still, we have to draw the structures for the sake of drawing structures. We have to. Again, we have CH3, then we have C, we have H, we have Cl, we have C, H, H, then we have C, H, H, and H. So a total of 1, 2, 3, 4. Wasn't it propane? This is for butane. So exceeding the number of carbon. This is propane, but increasing the valency of carbon. Carbon cannot have more than 3 bonds. Over here, there's a 4th bond with chlorine at the end as well. So that's also not possible. And this one over here is also not possible. Why? Because look, this is having only 2 carbon atoms. We had propane, I guess, and that's not possible. So the only possible answer is going to be option number A, 1, which was A, I guess. So this is going to be the only possible answer. All other answers are, impossible. This is not possible. 2 carbons, 1, 2, 3 carbons, but the valency exceeded over here. And over here, all the way we have 4 carbons. I don't know how. We had propane. So the correct answer is going to be option number A. Moving on to the next question. Okay. Now this one was a really tricky question. The diagram shows the structure of a compound called ethanoic anhydride. Okay, now this is something unknown that we guys don't know. No worries, we're going to stick to the basics and try to figure out as much as we can. Okay, 1 mole of ethanoic anhydride reacts with water to form 2 moles of carboxylic acid only. Okay, a lot of information to digest. That 1 mole of this thing, this one molecule is going to react with water. It's going to react with H2O to form 2 mole of carboxylic acid only. Nothing else is formed, only carboxylic acid is formed. This carboxylic acid reacts with ethanol to form an ester. Okay. How many moles of water react with 1 mole of ethanoic anhydride, and what is the structure of the ester? So this is a difficult question. Try to solve it yourself first. And if you figured out the answer, now let's discuss the correct answer. What you need to understand is, first you need to react this ethanoic anhydride with water to get your carboxylic acid. Okay, you need to make carboxylic acid out of it. Okay, it reacts with water to form carboxylic acid. So to make carboxylic acid, what do I need? I have a C double bond over here. I need to make 2 moles of my carboxylic acid. So I have 2 C double bond O. I'm going to break them from the center right here. I'm going to add an OH over here and an OH. I already have an O over here. I just need to add an H over here. Okay, I already, question has given me a no, I just need to add an H. So in total, what do I need to make an acid? Because this is the acid functional group, okay? The C double bond O with an OH is what I want, and over here as well C double bond O with an OH. So I just need one OH and one H. So in total, I need H2O. That's all what I need, and that's 1 mole of water. So how many moles of water do I need? I need 1 mole of water to convert it into an carboxylic acid. And what's the type of carboxylic acid I've made? I've made an acid. I've made 2 moles of the acid. Okay, I've made 2 moles of the acid with 2 carbon atoms. So I have made my ethanoic acid, and ethanoic acid plus ethanol is going to form ethyl ethanoate. And what is the formula for, or the structure for ethyl ethanoate? We're going to have not this. This is methyl propanoate, so that's incorrect. This is ethyl ethanoate, so it's going to be option B. We had 2 carbons in the in the acid thing and 2 carbons in the alcohol thing. So simple. The key concept over here was that you had to understand, to turn this into carboxylic acid, we need to break it, and we need 2H and 1 O, that makes it H2O, to get 2H, this H and this H and this O, to make 2 moles of acids. And ethanoic acid was formed. Ethanoic acid plus ethanol will form ethyl ethanoate, and we just had to figure out the correct formula. I guess we're done with this question. Let's move on to the next question, which says burning polymers can cause atmospheric pollution. Okay, we know. Which polymer on burning could produce nitrogen oxides? To produce nitrogen oxides, it should have nitrogen in it. So what has nitrogen? Polyethylene, no nitrogen, it just has carbon and hydrogen. Starch, it has CHNO, no nitrogen. Pterylene, it does not have nitrogen. Pterylene is a polyester, and now after syllabus changes, it's called PET. So no nitrogen. Nylon has nitrogen, it has amide linkages which contain nitrogen. So it's definitely going to be A, because we need nitrogen in it, and only nylon has nitrogen. And here we come to an end to all the difficult questions in this paper, and I hope you liked the video. Thanks for watching and subscribe to the channel. That's all for today.